All right, everybody, let's go ahead and do the paper 2. Just so you know, I'm going to do this in 2 parts because class will be starting in 54 minutes. So I'll do it in 2 things. Okay, so number 1 says a powder has the following percent composition by mass. It tells us it's 30% sucrose, 45% citric acid, and 25% sodium hydrogen carbonate. In the presence of water, the powder effervesces as the citric acid reacts with the sodium hydrocarbonate. So here's the reactants and the products. So for AI, it says, or I guess A1, it says determine the limiting reactant when 1 gram of this powder reacts. So we're given the percent by mass. Now notice here we got the sodium hydrogen carbonate and the citric acid. Sucrose doesn't show up, so we don't need it. I always recommend to look ahead a little bit because to determine the limiting reactant, we just have to find out how much of the products each of these reactants can make. Whichever one makes less is our limiting reactant, right? So we got 3 different products here. It doesn't matter which product we choose to determine what's limiting, but if we look ahead, eventually it's going to ask us for the volume of carbon dioxide produced. So it makes sense to go to carbon dioxide. All right, so if it's 45% citric acid and it's 1 gram, that means the mass of citric acid would be 0.450 grams. All right, so we just got to do a little bit of stoichiometry. The first thing I'm going to do is convert that to moles by dividing by the molar mass. So that'll tell us the mass of 1 mole of citric acid, which I'm just going to abbreviate Ca. So citric acid is C6H8O7, so 12.01 times 6 plus 8.08 for the 8 hydrogens plus 16 times 7. I get that the molar mass is 192.14 grams per mole. Now we use the equation that says for every 1 mole of citric acid, I produce 3 moles of CO2, and 0.45 divided by 192.14 times 3 equals 0.00. We got 3 sig figs in all our percentages. All right, so we're going to round to 3 sig figs, so it'll be 0.0703. All right, just to keep the video short, I'm going to pause it now and do the calculation for the other reactant. Okay, so I did the same calculation, but for 25% sodium hydrogen carbonate, and that was 0.0028 moles. So that means NaHCO4 is limiting. Okay, so that's how many moles of CO2 was formed. So if we look at part 2, it says determine the volume of CO2 released in A1. Use section 1 and 2 of the data booklet. Oh no, I closed all my data booklets. Oops, I had them all open. Whatever, we'll just use. I bet you, ooh, look at that misspelling from the past. That's the only thing we're going to get from section 1 is the equation, which in this case would be PV equals nRT. In section 2, what you're given is molar volume, which tells you that any ideal gas at STP is 22.7 cubic decimeters per mole. Now this does say here SATP conditions, but it's still 22.7 because of assumptions we make. So I just have to take the moles of CO2, which is 0.00298, and multiply by 22.7 cubic decimeters per mole. 0.00298 times 22.7 equals 0.0 to 3 sig figs, 676 cubic decimeters. And that's most likely our answer. I see 2 marks here. Just so you know, oh wait, hold on, I gotta go back to my thing. It says SATP, So I'm thinking one thing. Maybe we got to use PV equals nRT to determine the molar volume. So let's go back to the data booklet. At SATP, we've got 298 and 100 kPa's. So I'm just going to say here, just to be sure, because I don't get the mark scheme until the fall. So if the pressure is 100, we want to know what the volume would be for 1 mole of a gas. R is 8.31 at 298. So it's going to be 8.31 times 298 divided by 100, I guess. And that would be 24.8 cubic decimeters per mole, because this is at STP. So I bet you $10 they're going to want this 24.8. So let's change it. And that would actually give us 0.0739 cubic decimeters. If I were a betting man, I would say 1 for that, both for that. All right. Now, I went through this with my class. So you see how giving it a second look makes you think a little bit more carefully? Okay, so for number 1, part 3, it says calculate the percent yield obtained by a student who collected 0.043 cubic decimeters of carbon dioxide from 1 gram of the powder. So percentage yield, you probably recall, is the experimental value divided by the theoretical value times 100. Well, what we calculated in the previous problem was the theoretical, right? The experimental is what the kid got. So the kid got 0.043 cubic decimeters to 2 sig figs FYI. We got 0.0739 times 100. So we got just over 50. So 0.043 divided by 0.0739 times 100. Their percent yield was 58.2%. But since we're only given 2 sig figs in that value, I'm just going to say 58%. Report my percentage to 2 sig figs. Oops. Sorry if I go off screen. I'm thinking hard. State the number of acidic hydrogens. Well, and if the hydrogen is acidic, it will be in a carboxyl group. So there's 1, 2, 3. So the answer is 3. Deduce the structural formula of the conjugate base. So the conjugate base is the species that's produced when the acid loses a single proton. So just imagine taking that proton away. All right, so you just basically got to copy everything over. So we got our carboxyl group here, and then a bing a boom. We got a little bing there, and our OH. We got our carboxyl group up here. We still have the carbonyl and the oxygen, but the H is gone. Because this is a polyatomic ion, we have to put it all in brackets because it lost an H. It would have a charge of 1 minus. And that would be your conjugate base, because the other thing we produce is H plus. All right. Moving along, predict giving a reason the strength of the acid. Well, I would say that it is a weak acid. So remember, weak acids are weak because they are only partially dissociated. All right. Now, how do we know? Well, when you make the conjugate base, we lose 1 acidic hydrogen. There's 2 more there. So I'm not quite sure, but I'm pretty sure you might just need to say this. All right, why? But I would say only because 1 out of 3 H plus are produced, or something along those lines. Who knows what they're thinking until they tell us? Even the teachers don't know. Explain why sodium citrate solutions are basic. Well, remember, if citric acid is a weak acid, then that means the conjugate base is strongly basic. All right, remember, the weaker the acid, the stronger its conjugate base is. So because it's a weak acid, it's got a conjugate base. All right, so calculate the pH if the hydrogen ion concentration is that easy peasy. So pH is just the negative log of the concentration of hydrogen ions in solution. If the concentration is 0.0025, you just got to take the negative log of that. Negative log of 0.0025 is 2.60. 2 sig figs there, so I'm just going to say it's 2.6. Describe the bonding in solid sodium citrate. It is an ionic compound. And if you're asked to describe the bonding, it's basically just the definition. Ionic bonding is I'm going to pause while I write this out. Just trying to make this short. All right, so the definition is electrostatic attraction between oppositely charged ions. All of our bonding types are electrostatic attraction between. So for covalent bonding, it would be between a shared pair of electrons. Metallic bonding between a lattice of cations and delocalized electrons, or a sea of electrons. But this is ionic, so that's the definition. All right, state giving reason how the lattice and hydration enthalpies would differ if potassium ions were present instead of sodium ions. All right, so let me grab a data booklet here. Actually, you know what? I'll just grab, excuse me, the old school periodic table. This is from the pre-2016 curriculum. All right, so notice potassium is one box down in the group. That means it has one additional energy level. It's more shielded. All right, so lattice enthalpy would decrease. All right, and it's decreased because there is more shielding in potassium. Now for the hydration enthalpy, you could look in the data booklet, right? And you would see that, I'm just going to write delta H hydration would also decrease. I had a great reason for this in class yesterday, but I'm blanking now, so allow me to think for a moment. All right, I think what I would say is because of that shielding, hydration enthalpy is the enthalpy when the ions bond to water to make energy release. So I would say because of that shielding, I would say that the reason is probably the same for both, and that probably explains why it's 2 marks, 1 mark for both of those things and 1 for the explanation, just because it's the energy that's released when the bond forms because of the way the electrons work. So again, I don't know until I see the mark scheme, but we shall see. All right, on to question number 2. All right. So question number 2 looks like we have a little calorimetry experiment. Now, before we even look, let's see what we got. They're using this gel as a fuel, so they're going to set this on fire. All right, we have a calorimeter made of copper, not the best material to use for a calorimeter because it is a highly conductive to heat. So we're filled with water, and then we got a thermometer in there. Okay, so here in the table, let me adjust things a little bit. We've got the mass of water. Notice we have uncertainty values for each. I bet you we're going to need them. We've got the mass of water, the change in temperature of the water, the mass, and the initial and final mass of the gel. Okay, so when we're calculating heat, when we use section 1 and 2, section 1 gives us the equation we're going to use, Q equals MC delta T. And section 2, well, what does section 2 give us that's relevant here? The specific heat capacity of water, okay? All right, so let's go ahead and calculate Q. So we've got the mass of water, change in temperature of water, specific heat of water, so Q is going to be for water. So the mass of water is 400.00, right, times the specific heat, which is 4.18, times the change in temperature, which is final minus initial. 40 minus 19 is 21.0 Kelvin to 3 sig figs when we do the math here. I usually have a pre-made paper, but I gave it to someone yesterday. So times 21 equals 35,112. 5 sig figs there, 3 there. So it's going to be 35,100 joules. Calculate the percent uncertainty. All right, so look what we've done here. So for percent uncertainty, if we want the percent, that means, well, hold on, let me slow down. Percent uncertainty is the uncertainty over the measurement. All right, so we got to get the uncertainty of Q and divide by Q. Well, to get the uncertainty of a calculated value, we have to propagate the error. So the uncertainty of Q will be equal to our calculated value of Q times the percent uncertainties of all the values used to calculate it. So for the mass for water, so basically it's going to be Q times the uncertainty of mass over the mass plus the uncertainty of delta T over delta T. Now we don't include the specific heat here because specific heat is a constant. So let's go ahead and plug in our values. So it's going to be equal to Q, which was 35,100, times the uncertainty of the mass, which was 0.02, divided by the measurement, which was 400.00, plus the uncertainty of delta T. But remember, we subtracted to get delta T. And when you subtract or add, the absolute uncertainties add together. So the uncertainty of each temperature is 0.5, but of delta T, it would be 0.1, and divided by that measurement, which was 21.0. So when we do this math, it'll give us the uncertainty of Q, so 35,000 times 0.02 divided by 400 plus 0.1 divided by 21, and I get that the uncertainty is plus or minus 168.4. But we got to have it match the decimal places since that's a whole number. The uncertainty will be plus or minus 168 joules. So the percent uncertainty will be the uncertainty, which is 168, divided by the measurement, which is 35,100, and 168 divided by 35,100 is, don't forget it's a percentage, so times 100 is 0.478, which will actually round to 0.479%. Don't forget, we always multiply by 100 to get our percents. Again, don't quote me on this. It makes sense to me, though, because look at those percent uncertainties. 0.02 over 400 and 0.1 over 21. It makes sense that the uncertainty would be small. All right, for part number 3, it says, suggest a way to reduce random uncertainty. Well, if you're doing multiple trials and a random error occurs, it's not going to occur every single time. Now, this is a good thing because if you do more trials, you'll diminish the effect of that error. So if you ever see how do we reduce random, it's always conduct or do more trials. That says calculate the enthalpy of combustion, stating one assumption. All right, so enthalpy of combustion is the energy when we burn. It'll be the negative Q value divided by the number of moles of this substance. Okay. Now it's propan-1-ol. Now we're going to assume this gel consists only of propan-1-ol, but it wouldn't be a gel because propan-1-ol is a non-viscous liquid. Right? If this is a gel, there's something else in there to gelify it. But I'm assuming they're going to ask us about assumptions. That could be one that we make. All right, so the Q is pretty snappy. It'll be negative 35.1. Why not 35,100? Because we're starting with joules, but we want the enthalpy of combustion. It doesn't actually say in kilojoules, but we're going to calculate percent error. So it's going to be in kilojoules. Oh, never mind there. I was going to say, I could swear it asked us we need kilojoules. All right, now for N, well, what is N going to be? It's the number of moles of propanol. So to find that, we first have to find how much of the gel was used. Well, we started with 20 and ended up with 18.2. So we used, math, 1.80 grams of this gel. Yes, I can do math. All right, so then all we have to do is divide by the molar mass. So propanol, right, is CH3CH2CH2OH. So let's just add up the molar mass, 3 carbons. So 12.01 times 3. Plus 5, 7, 8 hydrogens, so plus 8.08. I feel like we already did this one. Plus 1 oxygen, which is 16. Don't forget to hit plus 16. And that gives us 60.11. Actually, I think propanol was used in a paper 1 I went over a couple weeks ago. So 1.8 divided by 60.11 gives us moles of propanol. That was 0 point to 3 sig figs, 0.299. So 0.3 as 0 moles. Plug that into there. Negative 35.1 divided by 0.03 equals negative 11,700 kilojoules per mole. That bell means I have 30 minutes till my next class, so I'll probably go for another 20, end it, and do the rest tomorrow morning. All right, so calculate the percentage error using section 13. So we just calculated experimentally the enthalpy of combustion. So when we go to table 13, what you'll see is the literature values for enthalpy of combustion. Yay, there we are. So this is propanol, there it is. The experimental value is 2021. So if we want the percent error, it's the opposite of percent yield. Okay, so let's do the percent yield and then just subtract from 100. So that is 2021. I'm just going to write this down here so I don't forget the number. All right, so for the percent yield, we got 1170. In reality, it's 2021. Multiply that by 100. 1170 divided by 2021 times 100 equals 57.9%. But remember, percent error is going to be 100 minus percent yield, and 100 minus 57.9 is 42.1%. Be careful here, you did percent yield, or on the previous page this is percent error. All right, suggest the main source of error. Well, check it out. Experimentally, we got 1170. Theoretically, it's 2021. So the main source of error is totally going to be heat loss. All right, suggest a way to use it or reduce it. I would say use a better calorimeter than copper. Use something like polystyrene, or use a bomb calorimeter. You could put a lid on it. Think of just ways to reduce the amount of heat that's lost while the reaction's happening. All right, part C says the student also investigates a second gel containing ethanol, sweet ethanol, with the same percentage by mass as the propanol in the first gel. Determine whether the second gel would release more or less energy per gram than the first gel. Use section 13. All right, so what I'm going to do is just write down here just so we can refer the standard enthalpy of combustion for propanol. I'll just say of P is negative 2021, and the standard enthalpy of combustion of ethanol is, well, we're going to get that from table 13. Where are you, ethanol? There you are, is negative 1367. All right, now they got the same percent mass. If it wants per gram, then what we should do is just divide by the molar masses, right? Because that'll be the energy released per mole, and then if we need to, we can convert to gram. All right, so again, I'm going to pause the video here while I work out the math, and then I'll explain it when I come back, just to keep the video not, under an hour. All right, so that's all done now. So if I take that's 2021, I screwed up. So if we look at the units here, if we take kilojoules per mole divided by grams per mole, the moles cancel and we get kilojoules per gram. So kilojoules divided by molar mass gives us 33.6 kilojoules per gram for propan-1-ol. When we do the same thing for ethanol, we get 31. So I would say that ethanol, the second gel, would release less energy per gram. Not all that much, but still less energy. Something tells me uno, dos, tres for the marks. All right, so ethanol and propan-1-ol are members of the same homologous series. State the names of the class of compounds and the functional group. The class are alcohols, and the functional group, the OH, is called a hydroxyl group. Something tells me you're not going to get it if you say hydroxide or hydroxide ions. State the strongest intermolecular force present in ethanol and propan-1-ol. They both have oxygen bonded to hydrogen, so the strongest intermolecular force is hydrogen bonding. Predict an intermolecular force that would be stronger in the next member, butan-1-ol. Well, butan-1-ol still has hydrogen bonding, but it's got 1 additional carbon and 3 additional hydrogens. Is that like a bump on my head, or just, it's just the glare. All right, anyways, so it has more electrons. So that would be the London dispersion force, or dipole-induced dipole, something like that. And the reason why is because there are more electrons in butan-1-ol. If there's more electrons, then there's a stronger overall van der Waals or London dispersion force, since it's caused by the movement of electrons. All right, butan-2-ol is optically active. Sketch 2 enantiomers. So I'm going to just draw a 2-dimensional representation of butan-2-ol. All right, so if you want to show the enantiomers, you have to show the 3-dimensional arrangement, or the stereochemistry. So what I would like to do is focus in on that 1 carbon and then set up your wedge and dash. All right, and then look what's bonded to that carbon atom. So this carbon atom has the hydroxyl group. It's got a hydrogen on one. It doesn't really matter where you put them. It's got a methyl group on one, which would be CH3, and an ethyl group on the other, which would be C2H5. So when we do the enantiomer, what we want to show is this reflected about this vertical axis. So here we have our carbon still in the middle, only here we have our OH. These don't really change position, so H and C2H5. Then we want to show our dash bond going to our methyl group, going the other way. Mirror images of one another. Deduce the organic product when butan-1-ol and butan-2-ol are separately heated under reflux. So reflux is important. With the butan-1-ol, the primary alcohol, if you heat under reflux, you're going to get the carboxylic acid. So in this case, it'll be butanoic acid. And butan-2-ol is a secondary, so you get butanone. Now you could have said but and 2-one, but the number's not necessary because there's no ambiguity. If that carbonyl group is on any carbon but carbon 2, then it's not a ketone, it's an aldehyde. Propan-1-ol can be produced from 1-chloropropane. That's going to be an SN2. So if we're going to replace the chlorine with the ol, the nucleophile would be OH minus. If you're going to name it, those would be hydroxide ions. Yeah. Remember, nucleophile means it's attracted to positive charge, so it's something that's negative. Sketch the mechanism of the reaction between 1-chloropropane and the nucleophile in F1 using curly arrows. So again, we want to show our 3-dimensional arrangement. This is 1-chloropropane. I myself like to put my leaving group on the right-facing bond. Just makes things easier. So if it's 1-chloropropane, not too shabby. This carbon will have, it's a methylene group, so it'll have hydrogens. We need 2 more carbons, so that'll be an ethyl group, C2H5. All right, now the first thing, I may as well switch up the color to show stuff. So we want to first show our nucleophile attacking. The nucleophile is a hydroxide ion. So you want to show that attack. The arrow will go either from the negative charge or one of the lone pairs and attack on the opposite side from the leaving group. That causes the leaving group to leave. Now, the SN2 is only a one-step process, but we have what's known as a transition state in the middle. Now, that transition state, you'll see why I do this in a second. We have to put it in square brackets because we have partial bonds to our nucleophile and our leaving group, and we show those bonds with dotted lines. Everything else just stays the same. So we got the H up here. We got our, I did not give myself a lot of space here, C2H5, and we got our H down here. So because we still have partial bonds to these things, we have one additional atom, which is why it's -1, because that -1 added. And then that's going to make our final product. Now we got to make sure we show the inversion of position. Since the attached nucleophile will be here, right? That stays the same. That stays the same, right? But we want to make sure, because we're going to flip the whole thing. I wish I made that a little bit further out. So, whatever. C2H5 and H. So mark 1, mark 2, and mark 3. Something tells me if you show the leaving group leaving there, you're not going to get that mark because this is the transition state between here and here. This has to happen before, this arrow has to happen before you get that. So you want to make sure you put the arrow in step 1. All right, next, ethyl ethanoate can be produced from ethene via a 3-step synthetic route. Let's just look what we got here. We got ethene, right? Reacting with water to make ethanol. That's an electrophilic addition. Here we have, oxidation of the primary alcohol into the carboxylic acid. And here we have the alcohol reacted with the carboxylic acid to make an ester. So step 1, the conditions, we need to add sulfuric acid, H2SO4. Now, some of my students said, what about heat? You could heat it to make it go faster, but putting sulfuric acid in water is a highly exothermic dissolution, so just adding it kind of produces the heat its own. Identify the reaction in step 3. That you could either say is an esterification, creating an ester, or you could call that a condensation reaction. And anyways, then identify the second product. Well, we call it a condensation reaction because liquid water forms. Now let me pause to see what those texts are about. Okay, I'm gonna just, I think I'm actually gonna stop here because I do have class starting in 17 minutes and I need time to eat my lunch. So we are about, seems like probably about 40% of the way done. And just based on what I've seen, the rest of this ain't too bad. So probably another 30 minutes tomorrow. So keep tuned for that. And thank you so much, as always, for watching my videos.